Okay, so today what we are discussing about the frequency response analysis, and we will discuss first the concept. What is this concept of frequency response? Okay, basically, the frequency response methods they were developed by Nyquist and Bode in 1940s. So, who are the two? There are two methods. They were developed by Nyquist and Bode. So they were developed by frequency response methods were developed by Nyquist and Bode in 1940s somewhere. They were developed by them 1930s. Sorry. Okay, and these methods, frequency response methods, are older as compared to the root locus methods. These are older as compared to root locus, which was developed by Ivan in somewhere in 1950s, 48 or 50s. Okay, 1950 it was developed. So two methods are there. Frequency response, Nyquist and Bode have developed them. So those methods we are going to see later on. Now what is happening here? During the steady state conditions, when we have a sinusoidal input to a linear system. So when we have a during what's happening now during steady state conditions, so when we steady state conditions, we are having a sinusoidal input. Sinusoidal input to linear systems, because we are discussing linear control system. So that's what. So whenever we have during steady state conditions, if we have a sinusoidal input we are giving to this linear type of control systems, then what's happening? They will generate also the sinusoidal responses. So what they are going to generate? They are going to generate sinusoidal responses, of same frequency. So frequency will also remain same. I'm repeating once again. So during steady state conditions, if we have a sinusoidal input we are giving to any sort of linear control system or a linear system, then as a result of the output, we are going to receive a response, or an output we are going to receive, but that output will be having the same frequency as that of the input. Okay, this is the first thing. Okay, even though these responses are of same frequency as that of as the input, even though responses will be having the same frequency as input, even these output responses will have same frequency as input. But what is going to happen here? One thing is going to happen, even though they will be having the same, they will differ in amplitude and phase angle from the input. I will again, during steady state conditions, we are giving an input to any linear control system. They are going to generate a sinusoidal responses, but the frequency is going to remain same. That is the first thing. Now, even though the frequency is same as that of input, but what is going to happen here? They will differ in amplitude and phase angle from the input. What they will differ in amplitude and phase angle from input. So this is going to happen main, although we are going to get the frequency output response, which will be having the same frequency, but only thing is that they will differ in terms of the magnitude, or we call it amplitude. They will differ in that, and also the phase angle from the input will be different. Now, before going to this frequency response in detail, let us first talk about convenient representation of the sinusoids. So what let me talk about before we define this complete frequency response, or we talk about this frequency response, let's look at the representation, how we represent this convenient representation of. Let's see what is the convenient, easy form we call convenient representation of sinusoids. Okay, convenient representation of the sinusoids. Sinusoids can be represented, if you know already, sinusoids, a basic electrical may be knowing, sinusoids can be represented as the complex number called phasors. We represent this sinusoids as complex numbers that we know in basic electrical, and we call them phasors, called phasors. So we will represent that by in terms of the complex numbers, and we call that complex numbers as phasors. Okay. The magnitude of the complex number is the amplitude of the sinusoid. So first thing here will be magnitude of complex number, that will be amplitude of the sinusoid. Amplitude of sinusoid. So this should be very clear. If we are representing them in terms of the complex numbers called phasors, then magnitude of the complex number will be same as the amplitude of the sinusoid, and the angle of similarly angle of a complex number will be what? That will be the phase angle of the sinusoid. That will be phase angle of. So this should be very clear. So magnitude of the complex number is amplitude of sinusoid, and angle of the complex number is the phase angle of the sinusoid. So that should be very clear. Now let's see. I have one system in front of me. Consider a system which is shown in figure. Now there is a figure A here. This is a figure A. Let's consider it figure A. This is a figure A. Now let's consider a figure which is shown here in the figure A. Now what is there? Input force F of t, which is here. See, you can see input force F of t. We call it is the sinusoidal. This is input force F of t is sinusoidal. The steady state output response, you can see here, the steady state output response X of t is also sinusoidal, and they are having the same frequency as that of the input. So what I have done here in this figure, we have first input force, just for the understanding of this frequency response. Input force F of t, it's a sinusoidal. The steady state output response X of t, output response X of t is also sinusoidal. And at the same frequency as input. So this we have already seen that they will be having the same frequency as that of the input. Now you can see this is a wall here and a spring is connected. This is a damper, and then mass is connected. We are having a sinusoidal force and sinusoidal response as a result of this. Now in this figure, input and output sinusoids will be represented by the complex numbers or the phasors. So input and output will be represented by phasors, which are nothing but complex numbers. We have seen that. We have to represent it like this. So input will be mi omega at an angle of theta I omega. So this is a magnitude and this is a phase angle of the input. And similarly, if you represent the output m naught of omega, omega is the frequency because frequency is same in both the cases. Response is output, input, and output response at the steady state, the frequency is the same. So that is phi naught of omega. So input and output will be represented like this. M, we know both the m's. What is this? Amplitude of sinusoid. We have already talked about it. These things will be different. Amplitude of a sinusoid. And if we talk about phi's, they are the phase angle of the sinusoids. Okay, this is the phase angle of the sinusoids. Now, let us see now, assume that the system is represented by the complex number. Now, transfer function type we see, or we say system is represented also by a complex number. And that is m of omega, that is angular frequency, at an angle of phi of omega. So this is, now we can see, we can always write from this figure number B, we can see this is an output response whose magnitude will be different, phase angle will be different than the input, but the frequencies will be same. And this is the system representation of a system, or in terms we can say a complex transfer function. We don't say like that, but we normally use the word system is represented by a complex number whose complex numbers whose magnitude is m omega and phi w, just like a transfer function. So how we normally represent this system now? We represent it output by m naught omega at an angle of phi naught omega, output by input, that is mi omega at an angle of phi I omega, is equal to transfer function. That means the system represented here is m of mw at an angle of phi of w. That's what we have represented the system. From this, what we can see, we can write output, we can write here from this equation. So this is simply output by input is system transfer function, that is system represented by a complex number. So here we can write output m of omega at an angle of phi naught of omega. I can write this will get multiplied there. So we have magnitudes, input m, input magnitude, and we have system magnitude, that means the transfer function magnitude. These two will go here and they will add each other. So we have phi of, because in polar form angles will add, phi of omega. So we can represent this like this. Let us say this is equation number 1. Tanzib,
Yes, sir.
this is clear up to here?
Yes, sir. Clear.
Okay. Now, from equation number, we can see that system is given by, we can see two things. M omega we have seen. If we take system is given by m of omega, okay, at an angle of phi of omega, that I will again repeat the above equation, will be equal to m naught of omega at an angle of phi naught of omega divided by mi of omega at an angle of phi of omega. Okay, now out of this equation, what I'm going to do, I am going to take the magnitude and angle separately. So m of omega can be represented as magnitude only, m of omega, m naught of omega divided by m input of omega. So let's call it equation number 2. Now second, what we are going to, phi of omega can be represented as You can see phi naught of omega divided by phi I of omega, which can also be written as in terms of polar phi of omega minus phi I of input of omega. Let us call it equation number third. Now, equation second and third, they will form our definition for the frequency response. They will equation 2 and 3, what they will form? They'll form our definition of frequency response. Now here what is going to happen? Here MW is the magnitude frequency response, we call it this MW. This is magnitude frequency response. And then phi W will be phase frequency response. Okay, phi W will be phase frequency response. This should be very clear. The combination of magnitude and phase frequency response is called the frequency response. So the combination of the magnitude and phase frequency response is called frequency response, and is given by m of omega at an angle of phi of omega. So you have to renamed it. So you have to remember it. So combination of both these magnitude frequency response and phase frequency response are called what? They're called frequency response. Now, if we talk about the definition, we define the term frequency response. So we will define the term frequency response, the steady state response of the system to the term frequency response is defined as, okay, it is defined as the frequency response. The term frequency response is defined as the steady state response of a system to a sinusoidal input. This is the definition. Or we can also write this definition as, first is very simple. Whatever the response will be, that will be at steady state. So that response will be sinusoidal, having the same frequency as that of the input. So that is called a frequency response. In frequency response, what we actually do, in frequency response, what we do normally, we vary the frequency of input, we vary, and what we are frequency of input signal over a certain range. So we will vary the input frequency over a certain range. Maybe we have some range 0 to infinity, 0 to something. So that frequency we are going to vary, and then we are going to study the resulting response, and then studying the resulting response. So this is what we are going to do in the frequency response. I will repeat it again. So we have to vary the frequency range input, whatever we are giving the sinusoidal input, the frequency of that input we are going to vary over a certain range wherever there is a possible to get the particular plot. Then we need to see what will be the resulting response of that we have to see. So that was an introduction about the frequency response. Now let's move ahead and we'll talk about we'll directly go to the polar plots. Okay. Next is our polar plot. So we have three plots: Nyquist, Bode, and polar. Polar is just a uh, just a part of the Nyquist. So next is, I hope till now there is no problem. Hmm? Okay, roll number 9.
Yes, sir.
Is it clear?
Yes, sir. Clear.
Okay. Next is the polar plots. Polar plots. Now have a look. What is this polar plot? Polar plot of a sinusoidal transfer function. Now I am using the word sinusoidal. I was using the transfer function earlier. Now I am using the, because I am giving the sinusoidal inputs to it. I am expecting also a sinusoidal response of a same frequency where the amplitude will vary and phase angle will also vary. So now I am using the word sinusoidal transfer function. So what I will write here, the polar plot of a sinusoidal transfer function. What is that? G of s is the normal S domain. Now s is equal to j s we will equate to s is equal to j omega. So that will become sinusoidal transfer function is what? Is a plot of magnitude g of jw. That is, it's a plot between what? It's a plot of, first part is magnitude of j of j omega, magnitude of the transfer function. We have to take which function? Sinusoidal transfer function will be there. We have to take the magnitude of that versus what? Versus the phase angle of g of jw. So this is a phase angle of g of, it's a magnitude of transfer function. Which transfer function? That's a sinusoidal transfer function. Against what we have to plot it? The phase angle of this sinusoidal transfer function, or on polar coordinates, on polar coordinates, as the value of the as the omega, that is frequency, will be varied from, is varied from the value of omega, that's angular frequency, is varied from 0 to infinity. So what is the polar plot? Polar plot of a sinusoidal function, whenever we talk about this, because we will talk about the sinusoidal transfer function, frequency response. So that is a plot of magnitude of the sinusoidal transfer function versus the phase angle of the transfer function. And we have to draw it on the polar coordinates. That means on the simple graphs, simple graph paper, we can draw it. And we have to vary the value of omega from 0 to infinity so that we can get a complete graph. So that this means that polar plot is a locus of vector, magnitude, and angle. Thus, we can also add, thus polar plot is a locus of vectors. Locus means path. Locus of vectors. Which vectors? Two vector we are using. G, magnitude of this sinusoidal transfer function at an angle. So this path we have to find. Path should be in this way. The polar plot is a locus of vectors g of magnitude of g of j omega and then angle of g of j omega as omega is varied from path is from 0 to infinity. Omega has to be varied from 0 to infinity. Now, polar plots, when we are drawing the polar plots, you have to note that in a polar plots, now you can be having a positive angle or you can also have a negative angle. If you have a positive angle, face angle will be measured, face angle will be measured in a counterclockwise direction. If we have polar plots, angle is negative, then face angle has to be measured in a clockwise direction from the positive real axis. That you already know. Angle is always with respect to real axis. So in polar plots, if we have to measure, that means what? If I am talking simply here, okay, then if this is 0, minus 90, minus 180, and this is minus 270, back to minus 360 is again 0. So this is in which direction? This is in minus. Minus is always clockwise. That's what I have written. So angle measurement has to be done like this. Now, if I will be taking counterclockwise direction, so then angles will be 0 and this will be plus 90 here and this will be plus 180 here and this will be plus 270 here and plus 360. So in that case, angle will be, measurement will be in the counterclockwise direction. That's what I'm saying here. So clockwise and counterclockwise is negative, counterclockwise is positive. This is the way we take it. First quadrant, second quadrant, third quadrant, and fourth quadrant. Okay. In summary, if I have to write, if I have to write, in polar plots, the magnitude of g of jw, h of jw is plotted against face angle of g of jw, h of jw. So that means in for various values of w that you know. In frequency response, what we have now? In frequency response, m, that is magnitude of j of jw, h of jw. That is the sinusoidal transfer function. Maybe that is a unity feedback. Then h of jw will be 1. So that is magnitude. And phi is angle of j of jw, h of jw, and that is the phase. Okay. We obtain the values of m and phi by varying the input frequency. The values of how we obtain these values, m and phi, values of m and phi are obtained by varying the input frequency. From input frequency is omega, that you always know, from 0 to infinity we have to vary it. So what should be the graph like? We can have a graph like this. Sorry, we can have a table like this. Okay. So if we have omega here, omega will be varied from 0, 1, 2, and up to infinity. So oh, sorry. Okay, if up to infinity we have, and then if magnitude we already know, magnitude is what? Modulus of g of jw, h of jw, that is modulus. And let us say values will be at 0, it will be m naught, m1, and so on and so forth. At it will be an m infinity, different values. So angles, phi will be angle j of jw, h of jw. This is the way we have to draw the graph. It will be phi naught, phi 1, and so on and so forth up to phi infinity. So this is the way we have to draw it. Okay, let's move. A very important thing what I have to discuss before taking any numericals. You should always remember that this is the way the graphs. This is a beginning of we draw just whenever we have to draw a Nyquist plot. That is beginning of that is a polar plot is a part of it. So that's why polar plot is very important for us also. Okay. Okay, so what is here in this case? We have the imaginary axis and we have the real axis. So we'll be taking both of them. So that will be a real part of the imaginary axis and other will be the imaginary part of the real axis. Just a second. Okay. So that will be r of g of h, so real, and this j will be imaginary of g of h. That's the open loop transfer function we are talking about. Okay. So we are talking about the open loop transfer function. Now you can have a look here. See, you should always remember type. I have already told what is the type. Okay, type and let me draw first, then I will. All are pointing towards origin. Later on, you can check it also, but if somebody has already checked it, he can memorize it like this. See, it is 0. So we have type 0 here, type 0. Okay. Then we have type 1 here in a counterclockwise direction, type 1. This is type 2. And this is your type 3. What is this type 1, type 2 I'm writing? Graph will begin of that. If type 0 is here, so it will start from here and it should end. I will tell you how it will end. And it should start from here. Type 1 will start from here. What is the type? So I hope you know. So we have number of poles at origin. That the power of s raised power n. Suppose we had a transfer function g of s equal to 1 by s plus 1. Then this is a at the origin, what is the power of the s? That is 1. So this is a type 1. If there will be no s raised power 0, so that will be type 0. So this is the way we define the, for your memory, we define the type 0 and type 1 systems. So type 1 will start from here, type 2 will start from here, type 3 will start from here, type 0 will start from here. Now order, so this is the order 1. Okay, order 1. This is your order 2. This is your order 3. This is your order 4 in the fourth quadrant in anti-clockwise again in anti-clockwise direction. So let me clarify what I am saying here. Some people may not get a clear picture of this. So where the graph has to begin, I have to look into two functions first. What is important for me to look into two functions? Let me take an example first. For example number 1, then we'll be drawing the questions. This much you have to know about the polar plot because this is the beginning. You will require this when you are drawing the Nyquist plot. So let us say an open loop transfer function g of s h of s is, I want to validate my point that what I have drawn here. You don't need to remember it, but if somebody wants to do a bit faster, he can always know, okay, type 0 will start from here, type 1 will, and so on and so forth. Let us validate this point. G of s h of s is 1 1 divided by 1 plus s of t. Okay, this is the transfer function given to us. Now, let's, so what you will be asked, you will asked to draw the, you will be asked to draw polar plot. Okay. Now I know this is type 0, asterisk power 0 is there, anything raised power 0 is 1. So this is type 0 system. Okay, what is the order? Order is also 1. Order means highest degree of S. So that is 1. So order is 1. So I already know this. Type is 0, order is 1. So I know this. This will begin from here and it will end here only. So that means the graph should, before drawing anything, I should know what I am doing. So before drawing, I know that this will begin in the quadrant number 1 and it will end also in the quadrant number 1 itself. So let us see. Now what I will do, I will take the magnitude of this. So let me put S is equal to JW because we are talking about the frequency response. Then G of JW, H of JW will be 1 by 1 plus JW T. So let me take the magnitude of this one. M is modulus of this one. That will be modulus of 1 by 1 plus j omega t, and which we know modulus 1 is 1, under root of the real part square is 1, imaginary will be omega square t square. So this is the magnitude. Let me take the phase angle of this one. So phase angle, this equation 1 I am talking about, phase will be, that will be angle j of jw. Okay, this was magnitude of, so this here you can write down, this was magnitude of j of jw, h of jw. This is what we are talking about. This is magnitude, this is phase. So now again what I have to do, angle of this, this has no imaginary part, 0, that will be itself 0. So then we have tan inverse of imaginary. If we will write 1 divided by tan inverse of imaginary by real. Imaginary is coefficient of j, that is omega t, by 1. So we can simply write angle is minus tan inverse of omega t. So this is the amplitude. Now I have to check how I don't need not to go for all the points. I will check 2 points, very important points for me. What are those? Now for, because omega has to be varied from 0 to infinity, I will check first point and last point. For omega equal to 0, what is the magnitude now? I will write like this. For omega equal to 0, so we have a value here. M will be, you can see here, I will put omega equal to 0. So this is 0, 1. You can see here. So omega, if I put 0, this 0 into t square is 0. 1 under root is 1, 1 by 1. So that will be 1. Okay. Now at this, I will write the magnitude also. This angle, what is omega angle? Angle will be phi will be equal to what? So phi at that point will be equal to minus tan inverse of 0. Minus tan inverse of 0 is 0. So phi will be minus tan inverse of 0 is 0. So I can write this as 1 at an angle of 0. So at omega equal to 0, magnitude is 1 and angle is 0. Next, for omega equal to infinity, these are 2 important points which will define the graph. For omega equal to infinity, okay, now you can write down omega equal to infinity. 1 by infinity is 0. So there is no question in that case. 1 is very smaller as compared to this infinity value. So that is infinity, that will be 1 by infinity is 0. So what will be phase angle? minus tan inverse of infinity. That is tan inverse of infinity is 90 degree. So this angle will be minus 90 degree. So here it will become 0 at an angle of minus 90 degree. So 2 points, vital points for me are at omega equal to 0. What I have 1 at an angle of 0, magnitude 1, angle 0. At omega equal to infinity, I have 0 magnitude and angle is minus 90 degree. So let me draw this graph here. Okay, sorry. Okay. Okay, so this is the real of this open loop transfer function g of h. This is j imaginary of g of h. Okay. Now you can very clearly see the magnitude is positive 1. Let me say the positive 1 is here. Let's say this is magnitude positive 1. So beginning positive 1, what is the angle? This is the value of omega. Let's say omega will vary. It will vary in the first quadrant only. Okay, because I am taking 0 and this I am taking reference as in counterclockwise direction. Minus 90, minus 180 and minus 270. I am taking like this. Okay. So magnitude is 1, angle is 0. So it will be first value will be omega will be here only. So that will be 1 at an angle of 0 here clearly. So here I can clearly say omega is equal to 0. There is no question in this case. 1 is the magnitude. Let's say magnitude up to here is 1. And angle, we don't have any angle because we have angle between 0 to 90. So angle is 0. I am writing that will be a reference angle. 0 angle is the reference angle. So moving to the omega equal to infinity. Omega equal to infinity, you can very clearly see angle is 90, but magnitude is 0. So that should be somewhere in the origin. So here it will be omega equal to infinity. Very clearly at this point, what is this point? So I will mark this point here. Very clearly at this point, magnitude is 0 and angle is infinity. So very clearly this graph will vary only from in one quadrant. That means it will start from type, because it's a type 0. Type 0 was here and order is also 1. It will end in this quadrant only. So graph is like this. In between values you can write. That's the curve will be like this. And that will start from this and move from 0. That's the point. That's the arrow. It will start from 0 and it will exit at infinity. This is very important while we are drawing it. Is there any questions? Row number 6.
Yes, sir. Clear.
Anything to understand? Any questions?
No, sir.
Okay. So this was one. Let me take another example. So now you can compare this with what I have shown here. Type 0 will start from here. Yeah, basically it will start from here. Yeah, it has started here. Order 1, it has to end here. If it is order 1, within this, it has to end here. Yeah, this has ended here. If you are in the examination, and if you are in the gate examination, you don't have to do anything. You have to just see which quadrant. If there are two options, then you have to only use this exact. But I don't think there will not be two options like that. There will be always single option and you have to take it. So you don't have to make any calculations. Next. Let me take an example, another example. Example number 2. Example number 2 is given is that open loop transfer function g of s h of s is 1 divided by s into 1 plus st. Okay. And we need to draw the polar plot. Okay, so let us see the solution of this one. So I know this is a type 1. Can clearly see s raised power value of that power on the pole at origin is 1. So this is type 1. And order is 2. Maximum power of 2 will be, maximum power of s will be 2. So order is 2. That will now already know. So type 1 will start from here. Yeah, you can see it. It will start from here. And order is what? Order is 2. This should also end here only. So it will start from here and end here only. Let us see. Type 1 and order 2. So let me first put S is equal to JW. So in a transfer function, open loop, G of JW, H of JW will be equal to 1 by JW, 1 plus J omega t. Okay. Now first is, let me find the magnitude. Magnitude is what? Magnitude of what? Magnitude of J of JW, H of JW. So this is the magnitude we have to take. 1 divided by, this will be omega. This will be under root of 1 plus omega square t square. Okay. So phi will be phase angle of G of JW, H of JW. So that will be, now if we go up, this is a 90 degree, or this will become minus 90 degrees, minus this will become tan inverse of, I am writing directly, I hope you know this, imaginary by real, that is 1. So this is your magnitude and phase. Now let us start substituting the value, two important values, that is omega equal to 0. At omega equal to 0, m will be, you can say 1 by omega is infinity. Okay, then what should be phi at that point? Minus 90 minus tan inverse of 0 is 0. So this will be minus 90 only. Okay, so now put omega equal to infinity. Two important points are for us. At infinity, magnitude will be 1 by infinity is 0. So phi will be minus 90 minus tan inverse of uh, minus tan inverse of what? Infinity. Tan inverse of infinity is 90, that we have already seen. So yes, tan inverse is 90. So that is 9 minus 90 and minus 90 degrees. This will be minus 180 degrees. So okay, now we'll draw the graph again. So from our calculations, it should start from here, type 1, and it should end here. This is our previous. Without calculating, we have to know this. But let us draw the actual graph. So drawing the graph again. Okay. So this is your real of G of H. This is of imaginary of G of H. Okay. Now first point is our infinity. Infinity. Sorry, here to write points here, just like previous. So this will become infinity at an angle of minus 90 degree. Okay. Just like this, infinity at an angle of minus 90 degree. So this will be 0 at an angle of minus 180 degree. These 2 points we have to plot. So infinity will, but it is coming from infinity. Okay, from 90. It is coming from infinity. So this is 0 degree minus 90 degree. I will write it for your convenience. Minus 270 degree, and again this is minus 360 is 0. We are going to have minus angles only because we have 90 and this. So infinity, I don't know where this is coming from. Definitely it is coming from somewhere here, infinity, but where it is going, I know that it is going to origin, and that is in 180 degrees. So it will in the second quadrant, 180 degrees. So I can draw it like this. So from here I will take like this graph, and I'm going to draw it like this. So this is the direction it will be moving. See, omega equal to 0. It's coming somewhere from infinity. We don't know where is infinity and where will be that omega equal to 0 in this case, but omega, it is coming from the value is coming from the infinity. Magnitude is coming from somewhere infinite value. So this is omega equal to 0 at. So this is here, this point here is omega equal to infinity. Its magnitude is 0. Yeah, this is the origin, and then it is exiting in the minus 180 degree, that is in the second quadrant also. So you can see from this graph also. So type 1 will start from here and it will order 2 will, if it is order 2, it will exit 3. If it is order 3, it will exit here. So that will depend on these things. So this is again the graph for this one. Okay, let's move to the third example. Okay, this. Now third example is example number third. I have open loop transfer function g of s, h of s is given as 1 divided by s into s plus 1 into s plus 2. Okay. So we need to again what? We need to draw polar plot. Okay. Solution of this is put s is equal to jw. So we have g of jw, h of jw equal to 1 divided by jw, jw plus 1, jw plus 2, j omega or jw we are using. Okay. Let us call this equation number 1. Let's move to the next page. Now let's see magnitude m, which is nothing but the magnitude of j of jw, h of jw. So that magnitude above will be 1 divided by omega under root of omega square plus 1 under root of omega square plus 4. So this will be magnitude. Okay, similarly, if I have to write phase angle for this one, phase angle will be angle of j of jw, h of jw, that will be, so if I take j will be minus 90 degrees, fine. If I take this here from equation number 1, tan inverse of imaginary by omega by 1, that will be tan inverse omega, but it will go up, minus tan inverse of omega minus tan inverse of omega by 2. Okay. Now here again we are going to find 2 points. Put omega equal to 0. So what we are going to get, magnitude is 0, infinity. First magnitude will be infinity, then phi will be minus 90. Tan 0 is 0, 0. So that is minus 90 only. So minus 90. So what is the point we have to draw here? Point is infinity at an angle of minus 90 degree. So second important point for us is omega is infinity. So magnitude here will be 0 because 1 by infinity is 0. So phi will be minus 90 minus tan inverse infinity. Tan inverse infinity is minus 90. Sorry, that's 90. 90, 90, that will be minus 270. So that is angle. What will be the point we have to plot? That will be 0 at an angle of minus 270 degrees. These are the two important points. So let us draw this. So what is this? We have not written order and this. Before we should have written, sorry. Okay, here it is type 1 and order is 3. Before drawing the graph, we should know where it will be. Type 1 is here. Okay, where is that? Here, type 1 is here, order is 3. So it should start from type 1 here and it should end in the quadrant number 3. Order 3 is here. From, if we are talking about if we are coming in the clockwise direction. See, we can draw the graph for this one. Okay, so this is our real of g of h. This is j imaginary of g of h. Okay. Now this is your 0 degree, minus 90 degree, minus 180 degree, minus 270 degree. and minus 360 degree is same as 0 degree. Okay. Now where we have to start? We have to start at infinity. Infinity we have to start, yeah, somewhere in the quadrant number here we have to start somewhere. It will be coming originating from here, but where we have to end? So omega 0, it will coming from the infinity in the 90-degree angle here, and it will be ending where? In 180 degree. Okay, so we have to start from here. The graph is not so good, but you have to draw it smooth. With the pen I cannot draw much smoother than this. Just a second, I'll try again. Okay, I'll try from here only, but you have to understood it is beginning is from there. Oh, sorry. Oh. Okay. So this is starting point our omega equal to 0. So this will be coming from here, and this is your omega equal to infinity. At omega, magnitude is 0, angle is 270. So 270 will come in this quadrant. But to be more precise, let us draw it like this. Just a second. Yeah, now this is perfect. Okay. So this is moving towards infinity here. So this is the graph we have to draw. Now sometimes what we need to do, if we have to find this point also, we can find this point also. How? Because this is a 180-degree line, and you can substitute in the magnitude condition, sorry, phase angle, you can substitute equal to this. Last time I have shown it, equal to minus 180 degree. Then you can find the value of omega. I'll repeat it again. If you have to find this point, you can find this point also. How? What's the way to find this? So what we have phi equal to minus 90 minus tan inverse of omega minus tan inverse of omega by 2. I think this is the one. Yeah. So we can substitute here minus face angle, because this is cutting at minus 180 degree. Face will be minus 180 degree. And from here, 90 degree minus tan inverse omega by 2. You can get the value of omega here will be somewhere around under root 2. So you last time I have done it one time, so same formula will be, same formulas will be used, so we don't need to calculate it here, it will take time. Then you have to substitute this omega equal to under root 2 radians per second. This is an angular frequency. So you have to substitute it where? In the magnitude. Magnitude is what? So you have to substitute, you'll get a point. M will be equal to 1 by under root of 2. Omega is there, I think, yeah. Under root of 2 square will be 2 plus 1 will be 3. Under root of again 2 square will be 2, and that will be 6. Yeah, 2 square under root 2 square is 2, and 4 plus 2 is 6. Under root 2 square is 2. 2 plus 1 is 3, and under root 2. So this will be 6. 1 by 6. Something will be 1 by 6. So what I am getting here, I think 0.85 something is there. I don't know how much is coming. Just check it. Under root 2. Okay, under root 2 square will be, yeah, something around this. You need to check it, please. Okay, so this point, which here it will be, so you can get this point somewhere 0.85 something is value. I think I'm wrong or correct. You can check this point. So you can find these points also. So this is the way you have to find how the graph will look like at the beginning. So this will be very helpful in the in case we are drawing the Nyquist plot, whether there will be lots of problems for the Nyquist plot. We need to know where the graph will begin and where it will end. Okay. So then, uh, how much time is Tanzim?
सर टाइम हो गया.
Okay, now we'll stop. So one more